Hello, everybody. Welcome to another episode together. And before we begin with regards to power and efficiency, I just want to clarify question number 8 in your homework, because it does reveal something very important with regards to things being launched. All right. With question number 8, we have an object that's being launched at the top of a cliff. All right. So it's going to be launched and it's going to fall. And the question is, how fast is it traveling when it's at this point over here? Okay. Now, to solve using conservation of energy, we know that at the beginning, you are 100 meters above ground. Okay, above wherever the ground is, which is beyond the PowerPoint screen. Okay. And the question is asking you, well, how fast is it moving right over here? How fast is it here? Okay. And this point in space and time, you're a quarter of the way down. In other words, your delta HF is equal to whatever you started off with, subtract a quarter of the way down, delta HI. In other words, it's going to be a whole subtract a quarter or 3/4 HI. So if you originally started off at 100 meters, 3/4 of the way down, you'd be down to 75 meters. Okay, so then now you have your delta HI and your delta HF for solving this. That's how you get to these numbers here in solving it. Okay, but let's just explain this question from a completely different perspective, because this answer can be solved whether if you use conservation of energy or kinematics. Okay, one thing that this question never mentioned about is how are you throwing this rock? Are you throwing it straight up and allowing it to come all the way back down, or are you throwing it straight down, or are you just throwing it at some weird projectile angle like that, or maybe even like that, or maybe you're even throwing it downwards like this? Okay, so you can see that there are many different outcomes here. Here's outcome 1, here's outcome 2, here's outcome 3, and outcomes 4 and 5, which is throwing it straight up or throwing it straight down, they end up in the same destination. All right, so with conservation of energy, you'll never know where you're going to land horizontally. It will never tell you that. Instead, what it'll tell you when you calculate this through, if you go through it properly, you're going to get a VF of 29.8 meters per second. In all of these 5 cases, they're all going to hit the ground at the same exact speed. Okay, so in all 5 cases, at that particular height, so 25 meters down from the top, they're all going to be traveling at 29.8 meters per second. The only difference is what angle did they hit the ground at. Conservation of energy, as it is a scalar quantity, it'll never tell you the vector answer. It's impossible. It's not by its nature. So if you are curious about how far it'll travel, where it will land, or the impact angle of its velocity, then yes, you have to switch over to kinematics. Kinematics will tell you the angle it's going to hit the ground at, and the magnitudes in either case are going to be identical. One student has a question.
For this unit, are we gonna have to switch over to kinematics at all, or are we just gonna stay in the
No, the purpose of this unit is conservation of energy, so we're going to treat it like this. Now, if you want to go one extra, then by all means, work through the single star and double star questions. The whole intent behind the single star and double star is to join all the previous ideas together. All right. So I know there might be a little bit of relief from some of you guys over here, but as I mentioned from the beginning of this course, physics is kind of like one huge jigsaw puzzle. Okay, it's one of the most complicated Sudoku puzzles you've ever had. There's bajillions of rules, but all the rules all point in the same direction to the same conclusive answer. And you can see what just happened over here. We're dealing with the same exact problem from 2 completely different perspectives. In fact, the technology is about 100 years apart. Right. With regards to kinematics, back in Galileo's time, yes, that would tell you where it's going to land specifically. But when you fast forward 100 years in the future, with regards to conservation energy, it still has the same answer. All right, so it's getting the same answer, but from a completely different perspective. Why am I sharing this whole story for you guys right now? Grade 11, yeah, we're going to be concrete about it. Okay, we're going to start off with kinematics, then dynamics, conservation of energy, so on and so forth. But by the time you reach grade 12, if you've heard, you're going to learn all of grade 11 all over again, which may sound easy, but here's the catch. You're going to learn grade 11 all over again where everybody's all put together. So in other words, you have to have the previous knowledge of how to solve this using all these different approaches towards solving a problem. Okay, so that's what you're to look forward to, I hope, in grade 12. You're going to see all these concepts one more time in grade 12, but you're going to see that at some point later in the school year, we're going to combine all these ideas together, just figure out, Johnny decides to go down a hill, the hill has a loop, and then the person takes off, and then the person lands, and then they land on a skid row with a certain coefficient of friction. And the question is, how far does a person skid before they come to a stop? All right, and in solving these problems, you need to pick up your skills from all these other ideas. Okay. So I guess that's a long-winded answer. Do we need to go back? Not yet. but in grade 12 you do. So if you want to prepare yourself for grade 12, I would encourage you to do the STAR questions, because the STAR questions require previous knowledge from kinematics. Okay, and I'll leave it with that. Yeah, we'll get started. How about we get started now? Okay, so here's our lesson on power and efficiency. And this little animation here is how I like to share with you guys with regards to what power is. Okay, so we have two clones of Kelvin and Hobbes. So we have team red and we have team blue. One of the problems of me trying to draw a picture is it's hard for you to see, what's going on here. But here's what's going to go on. Okay, we're going to have one team go up from the side of the hill, and the other team is just going to go straight up the hill. All right, so these are the two different pathways they're going to take. Okay, let's let it happen. Let's let the animation run. Okay, team red, you're up first. Yay, they made it to the top. Now it's team blue's turn. Team blue, make it to the top. Hooray, mission has accomplished. Now I'm going to go off into the polls. And before we go off answering anything, don't answer anything yet, guys. Use the polls. All right. And the question is I'll just write down blue, red, high. And the question is, which team does more work? Again, don't answer me directly. Instead, I'm going to save this. I'm going to launch it. And I want to see your poll. Okay. Which team does more work? Team red or team blue? Or is it going to be a tie in this case over here?
See the animation.
Guys,
how do we know what does what? We can't see the images.
Hold away.
But we can't see the images. Wait, how do we know what does what?
I can animate it one more time. No big deal. Okay. Again, we have team red who went straight up the hill. Team blue decided to roll themselves up the hill. And the question is, which team did more work? Team red, team blue, or is it a tie? I know, it's a very frustrating problem. I know. 14 votes so far. 17 votes so far. Okay, now I don't want this running on forever, so I'm going to have to end the polls very soon. Counting in 5, 4, 3, 2, 1, and I've ended the polls. And if you're able to see the polls, I have 11 students who believe Team Blue did more work, 5 believe that Team Red did more work, and 7 that believe that they tied at the end. And the funny thing about this is at the end of the day, they've both done the same amount of work. It is the same. All right. Now, yes, in reality, we'll probably see that Team Blue, they'll sweat a whole lot more trying to roll themselves up the hill. But again, that has to do with the inefficiencies of them. If you can imagine them as a sphere, then they wouldn't have an issue at all rolling up the hill. All right. Now, some people might think that as you go up a ramp, you're doing less work. But the truth is that when you go up a ramp to get to your destination versus lifting it straight upwards, yes, there's less effort in trying to go up a ramp, but you're covering a longer distance. So in other words, those two effects cancel each other out. Yes, you're sweating less as you're dragging it a longer distance because the force applied is lower, but you're carrying it a longer distance, and those two values cancel each other out. All right. So at the end of the day, it doesn't matter if you go up a ramp or you go straight up to the second height. Both objects will have done the same amount of mechanical work. Trick question. So how about another one? Okay, so I guess I gotta close this poll or start a new poll. Do I need to say anything? No, there is no poll here. You'll just see the animation. So let's just run through the animation. Again, just by the way how I've graphically drawn it, just trust me, they both start from the same altitude down below and they finish at the same altitude up above. It's just that I had to do it from a slightly angled view so that you can see that they are, side by side. That's all. But they're both starting at the same height and they're both finishing at the same height. And here's the next question. Which team does more work? Okay, we'll start off with that. And no, I'm not going to poll it. I'm just going to let it run. Yay, red team made it to the end. Yay, blue team made it to the end. All right, so if I ask you again, which team did more work? Well, they both traveled the same amount of height. So the work that they've done is exactly the same. But clearly, we've seen that there's a difference between these two. At the end, there's a good chance that Team Red would be sweating at the end and Team Blue would be a lot more casual about it. And that's part of it has to do with the efficiencies of our bodies again. But nevertheless, we see that there's a difference. And the clear difference between these two is the amount of time that it took for you to get your work done. All right. And that's when I introduced to you this next concept. We've talked about work already. Now let's talk about what power is. And power is related to time. So if you're wondering where do you start copying, here's where you start copying. Power by definition is the rate that work is being accomplished. It can be denoted by this formula here. Power is equal to work over time. And yes, it is true. Work has the same meaning as delta E, or change in energy. So you could also technically write it out as this as well. Power is equal to delta E over delta T. Well, when it comes to test time, I'm just going to give you the formula that's shaded in blue. So you'll get that official formula. And if you want to expand it out, then that's up to you. And it's really based upon the question that's given to you. Before we move on any further, I know there's an example question over here, and really you could just get started on copying on the example, but I just want to revisit what we talked about earlier one more time. All right, the differences between a fundamental unit and a derived unit. With regards to these fun and exciting fundamental units, again, for the purposes of high school, there are only 5. In truth, there are 7. All right, but for high school, we memorize it as the MKS system for high school physics. M for distance in meters, K for kg for mass. All right, so we measure masses in kilograms in physics class, and time is often simplified down to measurements in seconds. One thing I do want to point out, because I haven't emphasized it before, is that whenever you write down kilograms, always write it down as lowercase k, lowercase g. That's a proper definition for it, because lowercase k means take your measurement and multiply by 1,000. All right. If you write down capital K, lowercase g, it means a completely different unit. Because again, in high school, we cover 5 fundamental units. MKS, capital A for current, and temperature, if we borrow from chemistry class, temperature is not always measured in degrees Celsius. Sometimes it's measured in capital K. All right. So if you accidentally write down capital K on top up here, then it means Kelvin grams. And that's not what we're trying to get at for mass. Okay, so capital K is for Kelvin. Kelvin we'll discuss more in detail next week. Okay, so those are the fundamental units, and every other unit out there is based upon these fundamental units. All right, for example, speed. Speed is based upon distance over time. Acceleration is based upon distance over time over time. A Newton is equal to a kilogram times a meter per second squared, right? If force is equal to mass times acceleration, that's where you get the units from. And we just learned about work, right? Work is equal to force times distance. So a joule is equal to a Newton, where a Newton's equal to a kilogram times a meter per second squared times another distance, and that's why it's meters squared over seconds squared. And we mentioned about that in the last lesson. Well, here's a new one to add on to that list. So if you were copying this list away earlier, this is the new one to add on to it. Power. Power is measured in watts, right? And as we learned, power is equal to work over time. So effectively, we're taking a joule, and we're going to take a joule and divide it by yet another second. That's why in its fundamental units, it's going to be equal to kilograms times meters squared all over seconds cubed, because we're dividing by yet another time on top of work. Yes, a student has a question?
I pressed it by accident, sorry.
Okay. Okay. Any questions so far about this?
So what is work?
Work by definition is force times distance. Work is also the transfer of energy. Work is measured in joules. I know the letters do get rather confusing, and there is a summary table that you'll see in a future course pack where I just combine all those ideas together in one summary sheet, because I know the letters just go out of control. Okay, A is for current measured in amperes. We will cover amperes in a future unit. Okay, so that's what I said. For now, we're just dealing with just these 3 fundamental units. We will see A and capital K later on in this course. All right, so now you know the difference between a fundamental unit and what's on the left, which is a derived unit. Now, there is no derived unit for velocity or acceleration. We just know that velocity and acceleration are based upon fundamental units. But a Newton, a joule, and a watt, these are all examples of derived units. So I just wanted to point out that power is a derived unit. That's all I wanted to emphasize over here. I think there's one more question before I advance on. Is it seconds to the power of 3? It is. Seconds cubed. Okay. 1 watt is equal to a kilogram times meters squared over seconds cubed. All right. I'll leave it here for those that want to print screen it, but I need to erase this in 5, 4, 3, 2. Okay. Advancing onwards now. I just wanted to share with that yet again over here, and I'll probably emphasize this thing one more time in the future as well. Okay, so here is our first mathematical problem. What is the power of a person pushing a box 6.4 meters at a constant force of 525 newtons in 5 seconds? With all word problems, we always start off with what do we know? We start off with our givens. Okay, we know that the force applied is equal to 525 newtons, and the distance that the person has traveled is 6.4 meters. And this all happens in a duration of 5 seconds. Now, it's up to you how you decide to solve these problems here and beyond. Some people, what they'll do first is that they'll first figure out how much work was done. So they'll say work is equal to force applied times distance, and they'll multiply the 525 newtons by the 6.4 and get to an answer. And that's fine. And then you can sub it in to the next formula, which is power is equal to work over time. But optionally, this is what you could do as well. You can take these two equations and you can sub one into equation number 2 if you wanted to. So in other words, power is equal to force applied times distance divided by time. Now, if you're wondering, will this formula here be given to you on a test? No, that you will have to sit down and derive out. Okay, so if you want to derive it out from the beginning, you're more than welcome to. Alternatively, you could also just do it from first principles. Okay, just sub into the first equations, carry that number across. Just to maintain that consistent nomenclature of having equal signs more or less line up. Okay, make sure that you line up all your equal signs. All right, I still have students that don't line up their signs, their equal signs vertically. Why do you do that? There is a grammar reason behind it, but the other reason is so that it's easier on the eyes. Okay, so let's just take it from that perspective. It's easier on the eyes as opposed to the logical, rational reason. Okay, so work is equal to, yeah, force applied times distance over time, or 525 newtons times the distance of 6.4 meters all over 5.0 seconds. What does that equal? So 525 times 6.4 divided by 5 will give you an output of 672. Yes, technically speaking, it's 672, what is it? Kilograms times meters squared over seconds cubed. Technically, it is that. But again, that's quite the mouthful, saying that, you know, my car or that person has an output of 672 kilograms times meters squared over seconds cubed. It's just too many words to say. So that's why we have these derived units. It just cleans things up. All right. Since power is always going to be represented by those 3 units in that ratio, why not just call this a watt instead? Say what? And there you go. I do have this all cleaned up in the PowerPoint, so I'm just going to reveal that right now. It's the same exact representation. Okay. Now, if you're done with your activity over here and you take a look at your givens, 2 sig fig, 2 sig fig, then yeah, you probably would just round to 2 sig fig and call it quits at that point there. On a test, if you accidentally wrote down 672 watts, would I care? Probably not. I'll just let it be. Okay, so with that said and done, I just wanted to share with you guys other units that exist in the world, right? Because again, our neighbors to the south, they often go by a slightly different unit than what we do. And you've probably heard of that other unit before. For example, with regards to cars, cars are not measured in watts. Instead, they're measured in horsepower, all right? Horsepower, as the name implies, it is a measurement of power. It's just a power in reference to 1 horse. All right, so there is a conversion ratio. All right, how many watts are there in a horsepower? It's a fairly big number. It's 700 and change. Yeah, 746 watts for 1 horsepower. Okay, so if you were to try to convert this right now, because I know that for many of us, what is 672 watts? It's just a number for the most part. All right, 672 watts. If we convert to horsepower, then you can relate it to a huge beast here on Earth, and then realize that, whoa, that's quite a bit. Okay, so 672 watts. If we were to convert it to horsepower, we know that we need watts downstairs and horsepower upstairs. In 1 horsepower, there are 745 watts. So when you calculate this way through, since 672 is less than 745, you'd expect to have an answer that is less than 1. All right, and this is quite a bit of effort. Remember that 525 newtons is pretty much 525 crab apples. So imagine you trying to pull, and you had, let me just draw a little picture, okay? Let's say that you're standing over here, and you're pulling on a string. The string's connected to a pulley system where you have a big, big basket of 525 apples. Okay, so you're hauling 525 apples for a distance of 6.4 meters, and you're trying to do it in 5 seconds. Right, that's an average classroom in high school. You're trying to cover that in 5 seconds, and you're hauling a lot of mass. All right, 525 newtons. That's 52 kilograms approximately, almost the mass of a smaller high school student. Okay, so is it doable? Yeah, it's probably doable. I mean, if you've been working out every day and going to the gym, that's not a big deal. You probably could have a through output of almost 1 horsepower. Okay, but you're pretty jacked to do that. Okay, now can we do that indefinitely? No, you probably could only handle this for a couple of seconds, and then you're done. You're done for the rest of the day. You're spent. All right, but a horse has no problem at all doing this all day long and not get tired of it. And that's where 1 horsepower comes from. Okay, the definition of horsepower is the amount of power output by a horse if the horse had to pull something all day long without getting tired. And that's the value of 1. This was first researched by, guess who? James Watt. There you go. That's where the Watt originated from. Okay, so there is this background story about a horse. Instead of the horse pulling things, the horse is connected to an arm, and the arm is connected to a system which usually just grinds wheat. All right, so you're harnessing the mechanical energy of a horse to do something else somewhere downstairs on a lower floor level. Okay, in a factory or in a room. And they've noted that a horse has no problems at all pulling about the weight of a human being, around 180 pounds. Okay, so you can lift up a rather bulky high school student or a young adult. It can lift it up and have no problems of doing it all day long. That's how strong horses are. And that's the definition of 1 horsepower. They can handle it all day long, and here's the math that goes beyond it. Okay, so that's 1 horsepower. A horse being able to walk around this circle with a radius of 12 feet for the beam and walking it around 2.4 times per minute. And that's where the formula origin comes from. Will this show up on a test? Yeah, why not? No, it won't. Okay, it won't show up on a test. But again, I just wanted you to have a better appreciation of where these numbers come from. And because these are all weird decimal values, that's why we switched over to SI units, all right? Where power for our universe is equal to work over time, joules per second. Okay, now let's do another problem. What is the power of a person lifting a 100-kilogram box up 2 meters and doing it in 5 seconds? That's challenging as well. Wow, whole flight of stairs, 100 kilograms is like 210 pounds. So a pretty big football player in 5 seconds. Can a human being do it? I guess if you exercise enough, you probably could. Probably generate a very high amount of horsepower when you calculate it out, but you won't be able to sustain it for very long. So let's go and calculate it out. What does this measure out in watts? Okay, so we have a mass of 100 kilograms. The box is being lifted up 2.2 meters in 5 seconds. The fundamental formula for power is work over time. So we probably need to figure out the work in lifting something up, right? So work in lifting something up gravitationally, it will, at the end of the day, it'll be potential energy when you lift it up gravitationally. All right, so WG, work in lifting something up against gravity, well, that will be equivalent to mg delta H that we covered 2 lessons ago. Okay, so you have equation 1, and then you have equation number 2. Another way of seeing this is that, yeah, work by definition is change in energy. That is true. Okay, work is equal to change in energy. But remember, you started from the ground level. And if you're at ground level, your mgh at ground level is equal to 0. So that's why you're left with just mgh at the top when you sub in equation 1 into equation number 2. Okay, so yeah, work, which is equal to EPF, I guess, if you want to call it that, is equal to mg delta h. So when you sub them in, you end up with P is equal to mg delta h all over delta T. This equation, yes, it'll be given to you. Yes, I will give you this equation as well. I'll just call it EP. All right, but this third one, you'll have to know how to derive it yourself by equating one with the other. Next, we sub the values in. So a mass of 100 kilograms times 9.81 newtons per kilogram times a height of 2.2 meters. We're going to divide this over a duration of 5 seconds. You're fighting against gravity, right? Because you're lifting an object. When do we use EK and EP? Remember that EK is while something is in motion, and EP is you're lifting it against gravity and hoping to store that as potential energy at the end. Remember, when a person lifts the box up at that height, now that box contains potential energy. And if you're wondering, well, isn't it in motion while it's going up? That's true, but look at it this way. I lift it up, it's going to go up, and it's going to pause. In other words, at the end, when it's reached its final height, you're assuming the person has stopped lifting it up. So they're not contributing any more kinetic energy anymore. It's just strictly potential energy at the top. Because if there was still kinetic energy, then it'll just keep on moving up and up forever and ever and ever. Okay, and that would be weird. Okay, so this is an exercise which only lasts for 5 seconds, and then the person is done anyways. So we pull out our trusty calculator, and we do 100 times 9.81 times 2.2 divided by 5 seconds, and we get 431 watts. All right, so it's still a sizable amount of effort while doing this. Okay, with this completed so far, I just have 2 side questions for you guys. Number 1, what would happen to the work and power if instead of 5 seconds, it took now 10 seconds for it to accomplish? What would happen to the work?
Would work decrease?
Remember, you're still doing the same task. You're still lifting it up 2.2 meters.
The work is cut in half.
And that's why I like asking these questions here, right? There's always a common confusion with regards to this question over here. What will happen to the work if it took 10 seconds instead? Remember that the work that you're doing is just lifting the object up. It doesn't care about time.
Oh wait, yeah, never mind. The power is different.
All right. So the work would remain the same. Okay, the work value would be the same.
Oh yeah, but the power change. Oh my god. Oh
Yeah,
it just came to mind. Like we're talking about work, and so power is in watts, and work is in
joules.
joules. Okay, and then oh my god, because I'm getting mixed up with work and watts because they use the same for.
Yeah, I know.
My life right now.
It's a pretty big mess. In fact, I'll show you guys afterwards where you can find the summary table in case if you guys want that printed out for your reference. It doesn't bother me. Okay. All right. Same work, but half the power. That's what happens. Okay, so the work will be the same, but because you have twice as much time to go through it, you'll find out that instead of dividing by 5, now you're dividing over 10 seconds, that your power output is going to be half. And just to emphasize the thing I was talking about before, are you doing less work by going up a ramp? So let's say that you had a piano, all right, and you wanted to take this upright piano and you wanted to bring it up to the back of a lorry or of a truck, all right? One way of doing it is by physically lifting it up and then shoving it into the truck. And plan B is by pushing it up a ramp that has minimal friction. Who's doing more work? Ramp, lifting, or is the work identical? All right, it will be identical. Now, someone was asking, So someone's asking, what was the question? Do we need to assume up is positive? Now, here's the thing. It's you could assume up is positive. You could assume right is positive. Remember that positive work is when you're able to move an object in your favor. Okay. So in other words, when am I doing positive work in pushing this? Well, I'm doing positive work when I'm pushing it this way. I'm also doing positive work when I'm pushing it this way as well. And the reason for that is that the direction I'm pushing it at is the same direction that it travels. That's when I'm doing positive work. Okay, so that's the definition of positive work. Now, the weird one I know is like when you lift something up. Now, remember, as I'm lifting it up, I'm successfully lifting it up. And that's why I'm doing positive work as I'm successfully lifting it up. Now, as it's coming down, I'm trying to push it up, but I'm not strong enough. And that's why its gravitational weight is winning. Okay, so it's winning even though I'm pushing up. So now it's giving energy to me. If I was efficient and I had like a little elastic band in my arm, I'd be able to store it as a spring and launch it off afterwards. But with human beings, we're not efficient that way. We're still burning more calories while bringing it down. Okay, that's just the end result of us being who we are. Okay, but nevertheless, yes, this is positive work and this is negative work. And with negative work, all that's happening is that the object is now passing energy into its environment. So yeah, even though work and energy are scalar values, the plus and minus signs, they do bear a meaning. And often when you don't pay attention to that plus and minus sign, it makes everything else a lot more confusing. I have other episodes that talk about plus and minus work that's beyond the scope of this course, and you can go and check that out in the AP section. All right, so if you take a look at the AP Physics 2, it starts talking about thermodynamics, and in those episodes, you'll see parts that talk about, positive work and negative work when compressing gases or letting them expand. It does get rather messy, and you have to get your head right on, when is it doing positive work and when is it doing negative work. Otherwise, your answers will be in the wrong direction. Okay. Oh, when's the test? Oh, you're being tested at every single moment. Didn't I just test you guys right here? All right. As for when is the test, as I mentioned, if you go into the Google Classroom, that list has been in there since the beginning. We expect the test to be next week. Which day? I don't know. Look it up. Okay, it's there.
It's a
It is
quiz
there.
on Monday, and there's a test like on Tuesday, or was it Wednesday?
Whatever that's listed there. Okay. Whatever that's listed there. Remember that we're being recorded right now, so even though today is a Friday here, it's going to be a different day if I taught this on any other random day. So please, yes, thank you, student, for posting that up. All right, please refer to that for the schedule. I'm trying to stay true to that schedule. Okay, so for the second part of this episode here, all right, on efficiency, what exactly is efficiency? Now, you don't have to describe efficiency in any particular units because the units will divide each other out. So if you're talking about energy that's measured in joules, then it's a joule divided by joule multiplied by 100%. All right, so efficiency is a percentage. It's not any particular unit. So that's why efficiency can either be written out like this formula up here, or it could also be written out like this formula down below. As long as you're taking a measurement and you're dividing it by itself, then you're finding out the percentage efficiency. All right, so it could be energy out divided by energy in, or power out divided by power in, or even work out divided by work in. The formulas on the left are what's going to be written for you when it comes to your test time or quiz time. And as for the stuff that's written on the right, it's just for clarification because people wanted to know what exactly is E out. Well, E out is the useful energy that's outputted, that's being used by the system. Okay. Or being used by the task, not by the system, but by the task. Give you guys a moment just to jot down example number 3, and then we'll calculate it out. Okay. If you guys have ever swung a bat before, there is a sweet spot on the bat. And if you don't hit that sweet spot, it hurts a lot because all that energy is transferred back into your hand again. Okay. So let's start off with our givens. What do we know in this problem so far? All right. We know that the percentage efficiency is just 10%. The energy that's being put in so far is 40 joules, and I think intuitively you already know. If it's only 10% efficient, then out of 40 joules, only 4 joules goes into the ball. And I hope that logically makes sense, okay? If you put in 40% and it's only 10% efficient, you know that only 4 joules goes to the ball itself. Now, that's something that you would solve if it was a multiple choice question, but how would you solve this if it was a written problem? And that's why I want to go through the full solution. Okay, so that's what we're going to do right now. We're going to first figure out what the E out is using the proper formatting. So we'll start out with the formula. Oh, maybe I'll just rearrange it for you guys just to show you what's going on here. You know you're going to take this formula here, right? Because you're given energy in. That's how you decide whether to use power or energy. Here you're giving energy, so that's why you're going to choose that one. And we need to isolate for En. Okay, so the first thing we're going to do is that we're going to multiply both sides by En. So what you initially get is En times percentage EFF, that'll just be my short form for percentage efficiency, maybe we'll put in brackets just to clarify, is equal to E out. All right, and if you rearrange it the other way around, then that's what you get. E out is equal to En times percentage efficiency, and I forgot to get rid of the 100% by dividing both sides by it. Sorry, I forgot to do that, okay? Since that's multiplied by 100% on the right, you divide both sides by 100%. And that's how you get to the formula that's up above. Okay. I think for some of us, we just know the secret here already because with enough practice of rearranging a constant versus a fraction, these two people can swap partners and it'll always work. It's kind of like how, you know, sine of theta is equal to opposite over hypotenuse. With enough practice, if you're trying to solve for hypotenuse, it's opposite over sine of theta each and every single time you rearrange it. All right. And those shortcuts come from just doing homework multiple times. And through enough practice, you see these patterns. And these patterns help you become more efficient in the future. Okay, now we have the equation rearranged. We can now sub in the values. So the energy in of 40 joules multiplied by 10% divided by 100%. As we said, this is the long-winded way of getting to the answer, but this is the one with proper formatting. All right, so if I ask you to show all your work, then this is how you would show all your work. Otherwise, if it's a multiple choice question, I think that most of us know intuitively the answer was 4 joules, and then that effort in showing all your work wasn't all that necessary. Okay, now that we have the useful amount of energy, or useful amount of energy that is actually delivered into the ball, now let's figure out how fast the ball moves. Okay, so what values do we have? We know that the ball will now contain 4 joules of kinetic energy. We also know that the ball's mass is at 0.10 kilograms. And that's all we need to do to find out the speed of the corresponding ball. Okay. EK is equal to 1/2 mv squared. So when you isolate for V, just like in the example that I gave to you in the last slide, that's equal to 2 times EK divided by m, all square rooted. We sub the values in. So 2 times 4 joules divided by 0.1 kilogram. Crunch it away in our calculator. So it's the root of 8 over 0.1, and we get 28 meters per second. Is that right? Let me check with the answer key. Is it really 28 meters per second? No, 8.9. So what did I made a mistake somewhere? Oh, I forgot the open bracket. Open bracket of 8 divided by 0.1 close bracket will give you 8.9. Okay. All right. Remember that everything here has to be under brackets, and I forgot to open bracket it. So it did the root of 8 root of 8 divided by 0.1. Okay, so 8.9 meters per second is the valid answer, and that's totally fine. You can leave it at that. Now, the reason why I'm showing you all these other values over here is, once again, when I'm pointing out measurements don't really mean much to a person unless they can relate to it, all right? Like, for example, if I talk about the songs back in my days, if you guys haven't heard it, then you guys can't relate to the nostalgia behind it, all right? So if I tell you that a ball moves at 8.9 meters per second, Most people, even baseball player fans, will have no idea what 8.9 meters per second is. It's peanuts to them. Okay. Now, if I multiply that by 3.6, then I get it in kilometers per hour. So, okay, 32 kilometers per hour. That seems reasonably fast. In fact, a cyclist can normally ride at that speed. Okay, so if you pedal pretty hard and keep it maintained, you can easily well, not easily, but you can maintain a 32 kilometer per hour speed. So that's how fast the ball is moving. And for you big sports fans, as you may know, with certain baseball players, with the pitchers, they can easily throw a 100-mile-per-hour ball. So now when you look at the 20 miles per hour, you realize, oh man, that's wimpy. And that's why this ball won't travel very far at all if you try calculating it out. Okay, so yeah, when it comes to test time, yeah, you could leave it at 8.9 meters per second, but I'm just trying to relate to you that, sometimes you want to convert numbers into a value that others can appreciate and understand. And that's why I'm giving those other values. Oh, in kilometers per hour? Yeah, then you would. Sorry. Yes, I didn't even pay attention to my own question. Convert it into kilometers per hour. So you would multiply by 3.6. All right, so 8.9 meters per second times 3.6 will give it to you in kilometers per hour. I should have read my own question. Thank you for that. Any other questions, guys?
So in this case, E out would equal to EK?
Yeah, because remember, you're putting in 40 joules of effort, but because it's only 10% efficient, only 4 joules goes into the ball itself.
Oh, okay, got it. Thank you.
No problem. Any other questions? MPH, miles per hour, if you wanted to know. All right, in sports, balls are always measured in miles per hour, pitch balls. Why do we use EK? Because that's the formula. EK is equal to 1/2 mv squared. And remember, the energy out is attributed as the kinetic energy. We originally started off with 40 joules of energy. It was only 10% efficient, so only 4 joules was then delivered to the ball. How would you convert it? I think you multiply by 1.6, and that's a conversion ratio. Do we need to know that for a test? No. Yeah, again, I give that number just for reference sake, in case if those who are sports fans, then they're curious and, well, okay, 8.9 meters per second, what does it mean, right? It's just a number for most of us. But for those that can relate to one of these digits over here, it bears a lot more meaning. And that's why you would convert to a different unit, just one that your listener or your audience can better understand, and that's when you convert it. All right. For example, when you measure out, lengths of wood, you wouldn't measure it out in meters in construction. It's always measured in feet. It's just how it's done over there. Exactly. See, one person knows 20 miles per hour. Man, that's a wimpy ball that's being chucked. That's like someone just underhanding it. So the ball won't travel very far, and this poor bat swing would probably cause this person to be an out if somebody was close enough to catch the ball, that is. Okay. If there are any other questions, then I'd like to stop my recording. All right. Thank you for joining me in this episode. And for the next episode, yeah, make sure you do your homework. I think that's something I got to share with you. Bye now.